So if we get into a Python function, the signature looks like this, right? You have a def, and then you have the name of the function. We'll just call this function number. That's a good name for a function. And then inside you have these brackets, and then you have a colon, and then the body of the function goes in here. So you'd have whatever logic. We can even put that here. We can just say logic. The logic goes in here. And then you have an optional return statement. So that's another thing that's unique about Python. I mean, some languages have a similar characteristic, but if you don't return anything, there's an explicit return. And so by default, what Python will return is none. So if you don't tell it to return something, it'll return none. But you also can return something. So you can also say return and then put in some value inside, like X. And in the case of the input to the function, the input would be right here. You could do, Y and Z, right? And then inside of your logic, you would do something like, I don't know, Y plus Z, right? And then you could even have X is equal to Y plus Z. So there's not that many hooks in terms of doing things with a Python function. You can wrap the entire thing in your head very simply. It's really just a few different pieces, right? You have the definition, syntax, you have the input, right? Whether you're going to take an argument or not, and it could be either a keyword argument or it could be positional argument, whether it returns back explicitly or implicitly. And that's the basics of a Python function, which is one of the reasons why it makes it so powerful to build things out with Python functions. So that's probably enough theory to move on to actually writing some code. So let's go on and do that next. Let's say file, new notebook, and we'll call this one functions. And 2022. So let's start to build out some of the core components of a function. To start with, let's build the structure of our notebook. So we'll say functions, and then we'll make a subheading here called simple functions. And for the theory, the theory here actually, the Colab notebook is pretty good as well. So if I wanted to build the world's simplest function, it would look like this. We'll call this nothing. Right? That's the world's simplest function. It does nothing. It just returns a pass because Python implicitly will return nothing. And if I go through here and I call that function and I say value is equal to nothing, what do we get? Well, we can hover over it and it'll show us that none, right? So it's a none type none. So we know that that's one way to build a function, but usually people want to do something useful. So in order to do something useful, let's go ahead and build it out so that it returns something. So build another structure here, and we'll say return something. So we'll go through here, return something. Okay, let's say call this number. And so again, I have the syntax here, right? Def number. Let's make this a little bit bigger as well. Def number, and we can say return 1. So you can also just build a very simple function that that returns something. And if I invoke it and I hover over it, we see that that value will be 1, right? So it doesn't do much, but it does do an explicit return. Usually there's not really a reason to do something this simple, because just create a variable instead. And most of the time what you want to do is actually have some kind of logic inside. And so let's build another one called logic inside, and go through here. We'll say logic inside. I forgot if I made this one. Yeah, that's good. Logic inside. So for logic inside, let's do logic, and you could do something like x is equal to 1, y is equal to 2, and you could say return x plus y, right? So that's more of a traditional approach for a function that doesn't take input. And you could say, prints logic, and you need to actually invoke it. But basically, it calculates a value and returns back something. So this is something that is actually very, very common. Is you do a little bit of work in a function, maybe you throw it to 1,000 machines, and it returns back the result. But there's even another form of a function that is one that takes input. So let's go ahead and build that as well. So let's go through here. Input functions. And in this scenario, what we can do is make another one, and we can call this add. And kind of a traditional thing to do would be to take positional arguments. So positional means the first argument is handled, then the second argument. There's no explicit order, because they're not key value pairs. In this case, we could say calculation is equal to x plus y, and then we would return the calculation. And so now, if I go through and I call add, this would be 2 and 3, would be 5, right? So that's probably the most Swiss Army knife style thing you would do with a function in Python. One thing to note, though, is that we're missing a doc string that tells people what it does. And so we can do that, right? We can go through here and we can say complete function with documentation. And we'll do this. And we say def more add x and y. And here's where, especially as you get into more professional code, it's a good idea to document your functions. And you would add a triple, quotes here, and go ahead and say whatever it is you're gonna put in there. Say, this function adds values together, right? Or whatever it is that it does. And then we could do the same thing. We could say, even we can copy it. We can be lazy, and we can just return back the calculation. Perfect. And now, if we invoke this and we say result is equal to more add x, and we'll call this 2 and 2, we see that result is 4. And we also can do this. This is a neat little trick, is that if you say, once you add the doc strings, you can always do this, and it will show you out what is actually the documentation. So if you're building, I don't know, thousands and thousands of functions for some giant project you're working on, even if you never share it with anyone else, why not keep notes of what you're doing, I think it's always a good idea to have a little bit of documentation. It's just going to help you out. So that's probably the gist of like the basics of functions. The only thing we didn't cover would be two other scenarios. So let's cover a keyword arguments. So we'll do that next. Keyword arguments. So the difference would be if I just take this same function and we'll just say def keyword add, we could say x is equal to 1 and y is equal to 2. And we could again add documentation, say this is a keyword adder, keyword style add function. And the reason you would do this is that it sets default values for you. That's one reason to use keyword arguments. The other reason is that you don't have to worry about order anymore. If you were writing a function where order was important, then you can get yourself into trouble, because if you forget to put the first argument to the left and the second argument to the right, you cause you're going to cause some kind of a bug in your code. In this case, though, I can swap the order any way I want. It doesn't matter. And I can again do result is equal to x plus y, and then I can even print the result out here and say this is my result by using f strings. So I don't necessarily even have to return as well. Like it's up to you. It's your function, right? You can do anything you want. If we say keyword add here, this is my result. One other scenario that's kind of a cool scenario is the infinite arguments scenario, which is definitely kind of a cool technique. Let's cover that as well. And we'll cover infinite arguments. So how would we do this? If you wanted to have a function that could take anything, well, fortunately, it's not that hard. We would just say infinite, and we would just say asterisk asterisk keyword args like that. And this gets a little bit tricky because you have to handle the case for anything could be passed in. And so what you could do is you could loop, right, if you were going to do some kind of logic. So we could say first the documentation, this takes infinite. How do you spell infinite? Boy, I'm so bad at spelling. I'm so dependent on Google. There we go. I have to Google everything. Let's go back here. There we go. This takes infinite values or keyword arguments. There we go. And next up, I would just say for key value in keyword args dot items print key value, like that. There we go. And now if I call infinite, what do we do here? We just say x is equal to 1. There we go. Okay, but what if I want to make it something else? Well, we have infinite. We can do anything we want. We can say y is equal to 2. There we go. So it's kind of fun to play around with functions like that, where you can have like a dynamism to it, like, you know, right? Now, but you as the author of the function have to be able to handle those infinite values. So that's probably it. That's probably the basics of just like kind of the simple parts of functions. Now, there's more you can do though that's not simple, and let's cover some of the fancy things you can do with functions. And in order to do that, let's close all these down, and let's see how many. Let's call this simple functions. Top, like that, and then that way these are all hidden there. And then I want to do complex functions up here. And in this scenario, probably a good one to start out with in terms of complexity would be a decorator. So let's do that. Let's build a decorator. So the idea behind a decorator is that you have a function that wraps another function and basically is like a vine that is engulfing the other function. And I already have some examples here in another notebook, and I'm just gonna grab them and make it simple. So here we go. Let's just let's grab one of these things here, and yeah, so a timing decorator. This would be a good one. This would be a good one to grab. So I'm going to go over here, and we'll call this a timing decorator. So let's walk through the code here. We have a library function in Python called from functools import wraps from time import time. And so the way a decorator works is that you would essentially engulf the input of another function. And in this case, this wrap here, that's what the wraps does from the standard library. It allows us to preserve anything about the other function. And so in this case, we have args, we have keyword args. So basically it takes everything. And this is in a way like boilerplate. So you don't necessarily need to get too hung up on it. The only part that matters is this middle part, which is this is what you're going to inject inside of another function. And what this does is it calls time, which allows us to time how long a function would take. We also go through and we take the args and the keyword arguments, and then we take the end time. And really this just is a timer. It just says, okay, look, here's what you passed into the function, and here's how long it took. And so the reason for using this is if you just had this in, let's say, all of your notebooks, or maybe like a utility that you always imported in a project, anytime you were having trouble with something in terms of like performance, you would just put this on top and it would tell you exactly what's happening. So let's first do that. And then now to use it, all I need to do is just write some function. So let's write a function that sleeps for a little bit and has some input. We'll do like a calculation. So we'll say def calculation, or we'll call this slow calc. And what this will do is it will take an x is equal to 1000 and a y is equal to 2000, and I'm going to put the decorator on top here. So I'm going to say at timing, like that. And if I remember correctly, yeah, you just say at timing, and then we can put some documentation. It says this is a simulated slow calculation, like that. And then we would maybe add these numbers together. Result is equal to x plus y, and then we would return back result, right? So nothing fancy here, but it should give us some good stuff. And so now if I run this and I say slow calc, actually let's do one change. I forgot what to add is I'm going to add a sleep in here to simulate like a long time. So we'll say time.sleep. If I remember, did I import sleep from time? Yeah. So no, I need to import time again. So we'll say from time import sleep. There we go. And then we'll say sleep. And we'll just add like a 3-second sleep or something. 3, we'll say simulates slow calculation. Like if you're going to do something very mathematical calculation. There you go. So now if I say value equals slow calc, it's going to give us some cool stuff. There we go. So now see what it did? It printed out the name of the function, right? It showed us that there was, in this case, no arguments passed in, and it took 3 seconds. Now, the reason no arguments were passed in is that we had the default value. So if I change it and I say x is equal to 2 and y is equal to 3, and I run it again, then it'll show those calculations. There you go. X is equal to y is equal to 3. So really a quite useful utility for any Python programmer to have is to build your own debugging tools, right? And we could even make this, more sophisticated, like, or more implicit, like function name or something like that. We could, I don't know, like add more bells and whistles to it if we wanted to, like, for example, the doc string. That would be kind of a cool thing to add. And we could say print f doc string like that, and we could do this, and we could say f dot doc. So we run it again, run this again, run this again, and we should have even a little bit more. There we go. Pretty cool stuff, right? And so this shows the power of functions. We're just getting started with some of the really cool things that you can do with a function. Now, another complex thing that you can do with a function, I would say maybe one of the most complex things you can do with a function, is to build a closure, which is a function that retains another function inside of it. And so let's build that next. Let's do a closure like that. And now how would I build that? Well, let's go ahead and let's grab something I wrote earlier, and let's pass this inside of here. So here's a closure, and it's a lot of code, but it looks more complex than it is. Let's walk through it. So this is the function definition. It's an attack counter. Think of it as like the logic for a video game. Like when I was growing up in the 1980s, I used to play all those kind of video games like Street Fighter, and you would show how many times you would punch somebody or kick them or whatever. And so this would be like the logic behind a game like that. And here I have a variable that keeps track of the lower body counter. And then I have another variable that keeps track of the upper body counter. And inside, this is our attack filter, which is embedded. This is the function that's nested inside. And so why would you do this? So the idea is that the outer function creates a state that the inner function will use. And so it's a way of isolating the data that a function uses inside of itself. So I don't have to worry about global variables that could cause problems in code. I have my own data that I can actually access just inside of this one function. So for distributed computing, this is kind of a dream scenario. And so now what I would do is I would first take an input here, right, a parameter, which would be some kind of an attack. And then I have a non-local. So this means that only mutate this this value that's just one level above. Don't mutate something above, just one level above. And then all this does is it keeps track of, kind of different, mixed martial arts attacks. And it says if attack and attacks, if the attack is an upper body attack, then add 1. If it's a lower body attack, add 1. And then finally just show me the state of the world every time I run this. So if I get all this teed up, what would I do to run this? Well, first we have to make the function queued. So we'll say attack counter. So this basically creates the flow. And if I say type attack, we can see that in fact it returns a function. So even though I assigned a variable to the function, it itself returns a function, right? That's the whole point of a closure. But I believe as well, if I go attack dots, it should. You could get access to the state of the function. But let's just do this. Let's just call this, and we'll call this Kimura. So we'll say attack Kimura. There we go. We have an upper body attack. If I run it again, we have 2 upper body attacks, right? So it's keeping track of what it is that we're doing. And then if I add a lower body attack, it'll also keep track of that lower body attack, right? So there's some really neat little things you can do with functions, including closures, which is a great pattern for distributed computing. And not only that, but we can combine the 2 techniques, right? So we can combine the power of closures with the power of decorators. And I have an example here that I can use. And one of them is this concept of a randomized sleep. So let's grab this one. And let's do a randomized sleep decorator. Call this randomized sleep plus attack closure. So now we're getting really fancy. We're using closures and decorators at the same time. So what does this one do? So you can see here that there's again an outer function that has an inner function, and in this case, the big takeaway is that it adds some randomness to anybody that invokes it. So if I wanted to just, maybe I was doing some kind of like a chaos testing and chaos engineering, or I wanted to add some randomness to code to make sure that it runs in production under random conditions. I could add these decorators to do load testing, for example. And all I need to do is put this on top of my other function. So how would I do that? Well, I can go back to my other example here, and pretty easy. I can do this. I can say, let's build randomized speed attack decorator. So in this case, import attacks, random attack. So it's gonna basically yield a random attack, right? With sleeps. And then if I go through here, I can actually go in and add this code below. So this one will just say, attacking after 1 second, attacking after 3 seconds, attacking after 0 seconds, right? And what's cool about this is that in this case, I'm using this concept of a yield, which is basically a way of returning back values one at a time, which is a generator, which is also a neat technique to use in Python. So this is kind of the fancy stuff that you can do in Python. Probably one other fancy function that I'll build out is a partial, which also is kind of an interesting technique. So let's go through here, partial, and I think these come in very handy for doing data engineering. And so if we go through here and we add this up, let's go to partials and let's actually grab this. So the idea with a partial is you say from functools and import partial, and what this does is it allows us to call a function in a way that doesn't invoke it if I don't put all of the arguments into it. So this would be a great way to build like a pipeline of action. So let's say that I needed to do 4 different things every time I build a data engineering pipeline. I would not invoke the data engineering pipeline until the 4th action was called. And so it's a great way to kind of build, process control. And so in this case, if I made a function, a really, really simple function, and I said attack 1, attack 2, right? It doesn't do anything fancy. But if I run it like this, look, check out that I've put in run, make this function a partial, but only put in 1 value. And if I look at this, you can see that in fact it's a partial function. So how would we invoke this? Well, if I run 1 more value here, then it finally invokes it. And we can say, like, I don't know, leg lock or something. And there we go. So first attack, Kimura, second attack, leg lock. Now, let's make this actually a little more data engineering friendly. So let's rewrite it now and let's build a data engineering version of this. So we'll just call this data engineering pipeline. This is how I would see you would use something like this. So we would say from functools import partial, and then we would build out, ETL pipeline, right, like this. And then we would probably take in extract, load, transform, right? So this is the 3 steps of a data engineering or an ETL pipeline. So this is a pipeline partial function. There you go. So in this case, what we would do is print extract phase like this, and we would do that. We would say extract, and then we would say print f string load phase like that. And then we would do 1 more, and we would say transform phase. Now I'm just thinking out loud here, but one kind of a cool thing to do would be to put a timestamp inside of here. And I always forget how to do this in Python. So if I want to say import time to do, or let's use our friend Google, timestamp Python. Okay, we want to go for Stack Overflow. How do we get current time? There we go. That's what I want. Why use my brain if I can just use the internet? Perfect. So I want to do that, and then we want to do that. So let's take a look at that. And if we say now, And then if we want to say, and did they show me an easy formatting? Oh, print now. Okay. So you just do a print now. Let's do that. So if I say print now, that's pretty good. So yeah, we'll use that. So what I'm going to do is I'm going to put in the now when I call this function. And I think that's all I need up here. We've got that. We just need to put in transform. So what's cool about this is that if I want to invoke this thing and show when it was called, but then when it finally runs, this is a cool way to do it. So I could do this. I could say partial, and we'll call this pipeline, and we'll say partial ETL pipeline, right? So we know that that's a partial function. But now let's call them one at a time, but we'll pass in this thing, date time now, each time. So we'll do that. We'll say pipeline extract is equal to that. Oh, I need to call why is this missing two positional arguments? I think we need to do this. No. Load and transform. Why is my pipeline all of a sudden not working here? Let's take a look here. Import partial. I see. So check this. Oh, I know what I screwed up. I didn't do it like this. Let's go through here. Let's copy the style partial. Yeah, so let's first tee it up with the first one like that. Let's do two of them. Let's do two of them like that. And let's see how that. Okay, that works. There we go. We know it's a pipeline, and then we wait a few seconds, and then we run the last one. There we go. So kind of a cool example here where we say that the first phase and the second phase were run very close near each other, but look, this one is run slightly afterwards. So this is again just toying around a little bit with some of the things you could do, but in my mind, this could be a really clever, example of building out, like an ETL pipeline from zero. So that's good. I think we did complex Python functions and really cool stuff in here. And so, what can we cover next? Well, let's do like utilities, right? I think that would be a good example of some things we could cover next here. And so we'll do utilities in Python functions. All right, so one thing that came up was a YAML file. And so I can go back to a repo I have that has a bunch of code, functional intro to Python, and let's grab some stuff I did recently and working with files. Here we go. This would be a good one. So let's grab this notebook and I'll just refer to it. And again, this is why the table of contents, if you have a huge notebook, the table of contents is a huge win. So let's go down to save the YAML. Here we go. So we want to do some stuff with YAML. Okay, no problem. How do we do that? Well, first, we need to build out something like this. We need to make a dictionary. So let's build this out. So we want to build out like read a YAML file for read and write YAML, or just say read YAML. There we go. So first step, let's just make a dictionary. There we go. Next, let's go here and let's scroll down to importing YAML. So we'll grab a YAML, and then pretty straightforward is save the YAML, load YAML. If we want to load with open, right, save dump. Yeah, so first we need to save a YAML. So we need to do that first. So I'm going to have to read. Well, first we'll have to write our YAML. So we'll go through here. We'll say write a YAML. So go through here. And so what we do is we open a file called data.yaml. So we'll just make one programmatically. Obviously if it lived on disk, that would be fine, but we got to make one first. And I'm going to just do this. I'm going to say, basically write out my dict here, and then make a YAML file. There we go. And now if I just do a cat, I can actually just data.yaml, right? I can actually print it out. There we go. So we got a YAML file on disk. So that's how to write a YAML. Now let's read a YAML. So now we'll go to read a YAML. So to read a YAML, also pretty easy. Just do that with open, right? And then we just say res3. There you go. So pretty easy to read it in and then read it out as a dictionary. Now, we're covering functions though, so let's now convert it to a function. So how do we do this? Pretty straightforward. If I go to text here, let's do one more block, and we'll say read, I think that's maybe read a YAML function. Like that, read a YAML function. So what would we do? We could just say def read YAML, and we could just put in literally like YAML file like that, and then put a doc string that says this is my YAML reader function, like this. Unless we're not done. And now I need to put the code in that I had before. So I think it's oftentimes a good idea to build the statement first. If it's something that's a little bit complex, or you're just kind of learning the new logic or whatever, and we can just call this result. That's a better word, right? And so all this does is we use the with statement, which is it's like a shortcut for opening things. Because it adds a context, and we just load in that file off of disk. Now we need to change it though, so that it's this name. Pretty easy. We just swap it out. We just do that. We just say with open, and we say the result is YAML safe. And in fact, now all we need to do is say return. In fact, let's just call this YAML file, or YAML content. YAML content. There we go. And now, how would I run this thing? Well, I would just go in and say my YAML content is equal to read YAML, and then put in data.yaml. There we go. And now if I want to print my YAML content, there we go. Right, so this would be a nice little YAML function, and you could even, if you wanted to get fancy, add all kinds of things that we covered earlier, like decorators and closures and all kinds of stuff.